Hi, so the topic for today is reliability, and reliability, quite simply, is the probability that a system or a component of a system will work as expected. It is the probability that you'll get out of the system what you expect to get out, the quality, the time, and all of that. And so I've uploaded a separate video that introduces the concept of reliability, that introduces maintenance and how it interacts with reliability, and introduces some of the simple calculations like failure rates and failure rate n and mean time between failures. Those are in the other one. I just wanted to go through and give you some examples of reliability calculations because this is something that often confuses students. So the first thing is, let's talk about series reliability. And series reliability is the reliability of a system in which components are in sequence, so that the process involves one component and then a second component, and you have to go through both of them to finish. So it's often shown this way. You have component A and then you have component B, and to complete the process you have to go through both of them. So now we have a reliability of A is equal to 0.9, reliability of B is equal to 0.8, and so the reliability of the system is equal to RS is equal to RA times RB. So in this case, when things are in series, you multiply the reliabilities together. So if there was 5 items, you would multiply the reliabilities of all 5 of them together, because a probability is always between 0 and 1, a reliability is always between 0 and 1. The overall the reliability gets smaller and lower as you get more components, and so you want very highly reliable individual components in order that you get a reasonably reliable system. So in this case, the reliability of the system is equal to 0.9 times 0.8 is equal to 0.72, or 72%. So the reliability of the system goes down very quickly. Really, this is pretty straightforward calculations. The series calculations are dead simple. The only place that people go wrong is, I could say, look at this series reliability, but the failure rate of A is 10%. And failure rate is equal to 1 minus the reliability. So it is just 1 minus the reliability. So you've got the reliability 1 minus, so they have to sum to 1. So failure rate is the probability that the system fails, which is clearly 1 minus the probability that it works as expected. And so in this case, if I was to say the failure rate of A is 0.1, you would know to put 0.9 in there. And if I said here you have the reliability of A, the reliability of B in series, what is the failure rate of the system? You would do this math here, get 72%, and then do 1 minus 0.72 is equal to 0.24 is equal to 24%. So the failure rate of that system is 24%. That to me seems to be relatively straightforward. If I go back to 3 things, I have in series A, B, C, and you had 0.9, 0.8, and 0.9. The reliability of that system is equal to 0.9 times 0.8 times 0.9 is equal to 0.648. So you can see that the reliability of the system goes down very quickly, so that you want highly reliable components, or you have a system that only works 65% of the time. That causes us some grief. The next thing we're going to look at then is if you can't increase the reliability of individual components, you can build in redundancies. You can put in backups so that if A fails, there is another component that comes in and backs A up so that that step in the process doesn't fail. So we'll look at that, and so we have the same 0 A and B in series, and this was 0.9 and this is 0.8. We're going to back up A with component C, which has the same reliability. It doesn't need to have the same reliability. My example just does, and I'll show you that in the calculation. And we're going to back up B with D, which has a reliability of 0.8. So again, it is the same component. You're just putting a second one in. You don't have to go through all four of them. All this says is that you have to go from A to B, and if A fails, C will kick in to get, and if B fails, D will kick in. So there are two ways to calculate this reliability. The first one is the reliability of the system is equal to the reliability of A plus the reliability of C times 1 minus the reliability of A. So all this is saying is this reliability is A plus the reliability of C times the probability that C will have to come into play, which is the failure rate of A. So 90% of the time A is going to work, 10% of the time you're going to have to go use C, and then 90% of the time C is going to work. So failure rate of A times 90% will give you the reliability of this first step in the process, plus the reliability of B, plus the reliability of D, times 1 minus the reliability of B. So in this case, we'd have 0.9 plus 0.9 times 0.1, which is 1 minus 0.9. Like I said, in this example, the reliabilities are the same. They don't need to be, and then you just need to make sure which one you're doing. 0.8 plus 0.8 times 0.2. So the reliability of the first step in the process becomes 0.99. Clearly having that backup means we fail much less, times 0.96. So you can see how building a backup into this gets us to a much higher reliability very quickly. So that's why we build what's called redundancy or backups into the system. We can do the exact same thing, and I don't care which one you use. The reliability of the system is equal to 1 minus the failure rate of A times the failure rate of C, which will give you the exact times 1 minus the failure rate of B times the failure rate of D. So this is just looking at 1 minus the product of the two failure rates. This looks at the reliability plus the reliability of the backup times the failure rate of the primary component. They both will give you the same answer. You can use whichever approach you want. Is equal to 1 minus 0.1 times 0.1 times 1 minus 0.2 times 0.2 is equal to 0.95 or 95%. So you can use either approach, but you can see here very clearly that building that backup capability in gives you greater system reliability. I could do a system that looked like this: A, B, CD. So in this case, I have 3 steps in the process in series, and 1 step in the process has a backup. So here I have 0.9, 0.9, 0.95, 0.9. In this circumstance, we look at this parallel first, right? Before we do the series, we do the stuff that is in parallel. So step 1 would be the reliability of CD is equal to, and I'm going to just use this 1 minus the failure rate of C times the failure rate of D. Again, you can use either one of them, either approach is equal to 1 minus 0.1 times 0.1 is equal to 0.99. And then I do step 2, which is the reliability of the entire system, where I would do 0.9 from here times 0.95, which is B, times 0.99, which is CD, is equal to 0.802 or 80.2%. So in this circumstance, building that back up in, that's how we would calculate. We would calculate the components that are in parallel first, and then the series things afterwards. So here we're going to have, I'm going to just show you a couple of more examples, make sure I'm still aligned properly here. System A, we've got component 1, component 2, component 3, and we've got system B, which has component 1, component 2, component 3, and this one has a backup. So in this case, you've got, in the primary components, you have lower reliabilities, 0.99, 0.98, 0.985, 0.98. Which one would you guess would have the better reliability? Well, let's take a look at it. We would have RA is equal to 0.98 times 0.99 times 0.985 equals 0.956 or 95.6% for a failure rate of 4.4%. So then, do you think system B is going to be more or less reliable? Well, let's do the calculations. So in this circumstance, we look at these individual components in the parallel components in the series first. So then 2, the reliability of 2 is equal to 1 minus 0.98. I'm using the failure rate approach. 1 minus 0.95 equals 0.999 or 99.9%. So if we have 2 relatively high, but not as high as that, components in parallel, in backup, we get up very nicely to high reliabilities, and so we're higher than that. If we looked at the same thing, 1 minus 0.98 times 1 minus 0.95. So the backups in this case are lower reliability. Perhaps they're old versions and we're just using them for backups. Equals 0.999 or 99.9%. So even if the backup is inferior, we get considerably better performance right away. So then the reliability of B is equal to 0.98 times 0.999 times 0.999, which are the 3 components that are in series, is equal to 0.978 or 97.8%. So a much higher, well, a relatively higher reliability, and the failure rate of B is equal to 0.022 or 2.2%. So even though the individual components here are lower reliabilities, because we've built in that redundancy or that backup, it performs better. So I'm going to go through one more example that gives you a sense of the types of different questions you can ask. So you can say, a component must have reliability of 0.9925. So that's pretty high. So you have 2 technologies. One, R1 is equal to 0.999 and costs $2,000. 2, R2 is equal to 0.73 and costs $450. Which approach is cheaper? So we know that technology 1 meets our requirements right away. So we can spend $2,000 on technology 1 and we'll be there. Okay? So what we can also do is we can put several units of technology 2 together to have backup or redundancy, and as long as it takes fewer units to reach the threshold than the one to reach the threshold and have a total less than $2,000, we'll be better off with unit with technology 2. So let's take a look. If we had 2 units of 2, the reliability would equal to 1 minus 0.73, 1 minus 0.73 equals 0.927. Doesn't get us there. So we're not high enough yet. So then we'll go 3 units of 2. R is equal to 1 minus 0.73, 1 minus 0.73, 1 minus 0.73. We have 3 failure rates because we have 3 units, equals 0.980. So we still haven't gotten a high enough. So we still haven't gotten there. So let's try 4 units of 2. R is equal to 1 minus 0.73 times 1 minus 0.73 times 1 minus 0.73 times 1 minus 0.73. We then have it 4 times, and we just do that math very simply is equal to, so that's 1 minus 4 times the failure rates is equal to 0.9946. So now we've gotten to the reliability that we required through having redundant units of technology 2. We've achieved the reliability objective, and the cost of 4 units of 2 is equal to $1,800. So we are better off using 4 units of 2 than 1 unit of 1. So that's a quick introduction to reliability. It gives you an example of the types of questions you could be asked, and a couple of things to think about. Series reliability is the product. Parallel reliability, you do that other formula so that you find out that how much the backups improve your reliability of that step in the process. When you are calculating processes that have backups, you do the series first. Sorry, you do the parallels or the backups first, and then you do the series, and failure rate is 1 minus the reliability. Otherwise, this is relatively straightforward and shouldn't cause you any grief. Take a look at the other reliability video, and if you have any questions, please ask.